Okay, 25.3, the formation of images by a plane mirror. So plane again meaning just a flat mirror. So I want you to think about when you go to the bathroom, what do you see in the mirror? And as you reflect on it, you may notice certain qualities, right? So some observations. One, your right hand becomes the images, the person in the mirror's left hand. They're a mirror image of you, right? And this image, this person inside the mirror, is upright. They're still up like you are. They're even the same size as you, right? If you come up to the mirror, it matches up exactly. And the image is as far behind the mirror as you are in front of it. So as you get closer and closer to the mirror, the image gets closer and closer to you. Or as you're moving further and further away, the image is similarly moving further away. And that's, all of those are actually really key details to describing plane mirrors. And it's something, these factors are exploited with things like ambulances. So here's a picture of an ambulance. Great. And you may notice that it looks a little funny here. This is what it looks like if you walk up to an ambulance. You may not have noticed it before. I encourage you to check it out next time you get a chance to. So it's not an emergency situation, right? And why is that? Well, if you see it coming up behind you in your rear view mirror, you want to be able to read it, and it's going to be reversed left to right. So they purposely print the ambulance word backwards, reversed, so that when you look in your rear view mirror, you can read, oh, this is an ambulance, I better get out of the way, so they can get on their merry way. So there's a nifty little factoid for you. Now, a ray of light that is coming from the top of some object, like a chess piece, will reflect from the mirror, right? So we could imagine just drawing one of the light rays that's coming off of the chess piece, and it reflects off of the mirror, and it follows our law of reflection, right? Relative to this normal line drawn here, these two angles, theta, must be equal to each other. But to your eye, it looks like the light ray comes in a straight line from behind the mirror, because our eyes don't by default know physics. So they just assume the light ray must have just been traveling in a straight line forever, right? If it's coming straight at my eye, it must be coming from somewhere behind the mirror. And so the eye follows the light ray back and creates this virtual image of the chess piece that's behind the mirror. And the reason we call it virtual is because none of the rays actually emanate from the image, right? The rays that appear to be coming to our eye from this image are not actually real light, although light is on the left side of the mirror. So this virtual is something where there's no physical light there, but we see it there. And with mirrors, a virtual image will always occur when it's something behind the mirror or inside the mirror. So if you look inside at any time that you look at a plane mirror, you're looking at a virtual image. So think about that next time when you're brushing your teeth, that you are seeing this image of something where there's not actually physical light there. Now, you could do some analysis of the different light rays coming in, right? The light ray coming off of the chess piece to your eye, and hey, these thetas have to be equal. And thus, if you draw the dotted line of what your eye appears to see, you can convince yourself, and I'm going to skip that theorem, that the distance from the chess piece to the mirror needs to be the same as the distance from the mirror to the virtual image of the chess piece. So the way that we could write that in more formal terms is that the object distance, d sub o, is equal to negative d sub I, the distance to the image here. And the reason we have the negative is because it's behind the mirror, or it's virtual. That's something we're going to get more into at the very end of this chapter. For now, you just need to focus on the fact that the magnitude of these distances is the same, and will always be the same anytime we have a plane simple mirror like this one. Now, there still are some interesting things we can do here. Just because it's a plane mirror doesn't mean it's a plain and boring mirror, right? So we could look at mirrors and say, hey, what's the minimum mirror height necessary for someone to see their full image in a mirror? Do they need the full length mirror to be able to see their, from head to toe, what they look like? And so what it turns out is if you look at it, your eye looking up at yourself, right, to see the top of your head, only has to go up to point P on the mirror, right? If you focused your eye on point D, then you'd be reflecting on something above your head. But by your eye looking at point P, that's just the right angle to see the top of your head. Similarly, your eye can focus in at point B, and that will give you just the right reflection to see down to your feet, following, which is point F, right? Following the law of reflection. And we could see that in the image, right? The light ray would go a straight line down to the feet, which the person's at the equal distance behind the mirror as the person is in front of the mirror. If it looked any lower than point B, they'd just be seeing the carpet in front of the mirror, which isn't as helpful. What this means is that they only need this top portion of the mirror in order to see their entire length, right? So here's another depiction of it where a man looking in the mirror, right, can see the top of his head going to his eye or the bottom of his feet going to his eye, and only needs this portion in green of the mirror. Doesn't need the very top of the mirror or the very bottom of the mirror. Now, where this does matter is you might need to have that half mirror at different heights because everyone is at a different height, and it's half the height of the person. So if you have a taller person, you're going to need a longer mirror than a shorter person. But that's a pretty nifty application that, yeah, you could cover up the bottom part of your mirror and still be able to see your feet. Another conceptual example we could look at here is multiple reflections. So here we have a person sitting in front of two mirrors that intersect at a right angle. So they're just coming in like this. It's only two mirrors here. But the person, instead of seeing two images of herself, sees three images of herself. So think for a moment, and you can pause. Why are there three rather than two images? Well, you may have guessed it. The key is that you get some reflection for these first two images. It's just a straight reflection as before. For the third image, you're getting a reflection of the reflection. In other words, the image created in the one mirror can then become a reflect into the third mirror, or here it's drawn reflecting off mirror one and then reflecting off mirror two, and it appears to be coming from a third image within the mirror, which is pretty trippy. It's what fun houses take advantage of, right? Where instead of seeing one of you, all of a sudden there's three of you. Which one's real? That's getting a little bit too metaphysical. So we will pause there.